So welcome to week 6. You've survived weeks 1 through 5, so hopefully we've kept your attention. Now, when someone gives a talk, say an interview talk for a faculty position here, the rule of thumb is that you should give a talk that everybody in the audience can follow along with for about 40 minutes. And then the last 10 minutes you get to wow the experts. Well, week 6 is that wowing of the experts, except that in this particular case we have made you the expert, and therefore you'll just be there with us and everything will be crystal clear to you. So, I'm going to motivate this week by looking at an operation that you may have seen in high school or in some other linear algebra course. We certainly spent quite a bit of time on it in our first MOOC, Linear Algebra Foundations to Frontiers. And let's just go and have a look and see what it is that you were originally taught. Okay, so what do we have here? We have 3 equations in 3 unknowns, 3 linear equations in 3 unknowns. And somewhere in your math career you were taught how to solve this. Okay, what were you taught? Well, you can take multiples of rows and add or subtract them off of other rows and not change the solution. Unless you multiply by 0, but we're not going to do that. So how would you do that? Well, you would take the first row and add it to the second row, and that would take this term away, and then you would take 2 times the first row and subtract it off of the last row, and that would take that term away, and then you would be left with a smaller system of 2 equations and 2 unknowns, and then you would take a multiple of this equation and subtract it from that equation, and eventually what you would end up with is an upper triangular system, and then you could solve for z, and once you know what z is, you could solve for y, and once you know what y is, you know what z and y are, and therefore you can solve for x. Coming back to you? Okay, now, because it was a lot of bother carrying all of these symbols x, y, and z around, what you were then told was to say, well, create a 2-dimensional array with the coefficients. So we would end up with 1, minus 2, 3, minus 1, 1, minus 2, 2, minus 2, 6. And you recognize that this simply captures everything that's up here. And then you may have been told, and then append the right-hand side like that. And now what you can do is just do multiples of the rows of coefficients as you go along, instead of also having to write these x, y's, and z's around. And lo and behold, this may have been your first exposure to what was then called a matrix. Okay? So this may come back to you. Okay, so what did we then do with this? Well, this is going to be a little hard to keep track of because I want to always think in terms of subtracting a row from another row. And as a result, we're going to take the negative sometimes and sometimes the positive. So hang in there as I do this, okay? So, what can we do? Well, we can take minus 1 times the first row and subtract it off of this row. Okay, so let's write that down somewhere. We'll write it down here. Minus 1 times the first row is being subtracted off of the second row, and of course that just means that we take the first row and we add it to the second row, right? Okay, so that becomes a 0, that is added to that and becomes a minus 1, that is added to that and becomes a 1, that is added to that and becomes a 3. Okay, so far so good. Then we need to take 2 times the first row and subtract it off of the last row. Okay, so we'll write down a 2 here. And what? Well, that becomes a 0. 2 times that subtracted from that means that this becomes a 2. 2 times that subtracted from that becomes a 0. 2 times that subtracted from that becomes a minus 4. Okay? And then what? Then we say, okay, we can think of this as a smaller subsystem. And then what? Then we can do minus 2 times this row subtracted from that row, which of course is the same as doing 2 times this row and adding it to that row. And if you do 2 times this and add it to that, you get 0. If you do 2 times that and add it to that, you get 2. And if you do 2 times that and add it to that, you get 2. Okay? And then you notice that this is an upper triangular system, and you can say, oh, this really represents 2 times z, so z is really 2 divided by 2 and therefore 1, and then you can take that and plug it in here and say, oh, minus 1 times y plus 1 must be equal to 3, and you can compute y out of that, etc. All right? So let's take that away. Now here is the magic. Okay? Let's go back up here and let's think back of the matrix that we had there. And let's write it over here. 1 minus 2, 3 minus 1, 1 minus 2, 2 minus 2, 6. And let's take this and let's write it over here. Minus 1, 2, minus 2. And let's take this upper triangular matrix and let's write it here. 1, minus 2, 3, minus 1, 1, 2 with zeros below the diagonal. Okay? Now this is the part that always makes me feel like a magician, okay? Nothing up my sleeves. Here we go. If we go and we put 1s on the diagonal in this matrix, and we put zeros above the diagonal, then magic, if you multiply this matrix times that matrix, you get that matrix. Okay? So, this we can refer to as a unit lower triangular matrix. It's got 1s on the diagonal, and that's what we call a unit lower triangular matrix. This we can refer to as an upper triangular matrix, and what we're saying is if you compute L times U, you get back A. And this then is known as the LU factorization of matrix A. Okay. And it turns out that you can compute the LU factorization of matrix A, and then you can do other things with that. For example, you can use it to solve linear systems, etc. Okay, and how that all fits in, you'll see later in the week. Now, what do we do in this course? We do goal-oriented programming. What if we make our precondition A is equal to A hat? And what if we make our postcondition A contains L and U? Let's write that like that with kind of a funny slash here. Where and L times matrix U is equal to the original contents of A. Now, what do we mean by this particular notation here? Well, notice that you could take these entries here and put them right there, and in effect store L and U both in the same matrix by virtue of the fact that you know that the diagonal elements of L are 1, and therefore you don't need to store them. And what that means is that you can take the result of computing the LU factorization and you can have it overwrite the original matrix so that you don't need additional space for the result. And that's typically how it's done. People who do numerical computing are typically very stingy with memory. They want memory to be used for useful things, and therefore if you compute the LU factorization of matrix A, you want to in place replace A with the result so that you don't need additional memory. Now, over the years, different algorithms for computing the LU factorization have been found, inspired by different ways in which this computation can be arranged. And as a matter of fact, over the years, since this is sometimes referred to as Gaussian elimination was invented, 5 different algorithms came out. Okay, and so every couple of decades somebody would find another algorithm. What you're going to find out is that in about a half an hour, with the tools that we've given you, you can derive all 5 of those algorithms off the bat. And then you can go a step further and derive blocked algorithms that will attain high performance and implement them, and you're done. Okay? And that kind of gives you an idea of the power of what we have now given to you. Okay, let's get started.